Hello and welcome to today's video. Self-supervised learning has become dominated by a patchwork of heuristics. For years, joint embedding predictive architectures have shaped modern AI, but they suffer from a core issue: representation collapse. To avoid it, the field piled on workaround after workaround: normalization tricks, whitening, asymmetric views, and the well-known stop gradient. Often we rely on complex teacher-student setups with fragile EMA tuning. It's messy, it's brittle, and it's not scaling gracefully. So the real question is, what happens when a tower built from complexity begins to crumble? This tower of heuristics isn't just complicated, it's unstable. Current LeJEPA training is extremely sensitive. A tiny hyperparameter change can cause the whole system to fail. Many anti-collapse tricks even require quadratic memory or compute, which makes scaling painful. And because there's no solid theoretical grounding, progress feels like playing whack-a-mole. To break the cycle, the authors stopped treating symptoms and asked a deeper, foundational question. For years, we kept adding fixes, but no one asked the axiomatic question. The issue isn't just the tricks, it's that we never defined what the embedding distribution should be. So the authors stepped back and started from first principles. They asked, what is the optimal distribution of embeddings that minimizes worst-case prediction risk across every possible downstream task? The answer, derived cleanly and mathematically, is surprisingly simple. That answer is the isotropic Gaussian. The authors proved that this distribution uniquely minimizes downstream prediction risk by balancing bias and variance. Whether you probe the model with linear methods or nonlinear ones like KNN or kernel functions, isotropy gives you the most reliable predictions. By forcing representations into this clean spherical shape, we set the network up for success across any future task. And the impact on training stability is dramatic. Here's why anisotropy is dangerous. On the left, perfectly isotropic features lead to tight, confident decision boundaries with very low variance. On the right, an anisotropic distribution stretches and distorts the space, causing the classifier's boundaries to scatter wildly. Variance jumps from a tiny 0.005 to more than 0.08. This stretching amplifies both bias and variance, making learning unstable. So the natural question is, how do we reliably force high-dimensional neural features into this ideal spherical shape? The solution is SIGReg, Sketched Isotropic Gaussian Regularization. Instead of matching the full high-dimensional distribution, which is impossible, SIGReg uses random projections. It takes the embedding space and looks at it through many one-dimensional shadows. If all those shadows match the ideal one-dimensional Gaussian, then the full distribution must match as well. This idea relies on a clever extension of the Cramer-Wold theorem and gives us a powerful way to enforce isotropy at scale. SIGReg is provable, stable, and scalable. It runs in linear time and linear memory. The Epps-Pulley characteristic function test ensures that gradients remain uniformly bounded, eliminating the instability found in moment matching or whitening-based techniques. And because the characteristic function is just an average of exponentials, SIGReg works beautifully with distributed training using all reduce. It also avoids the curse of dimensionality by requiring projections that scale gracefully with smoothness. This creates a robust foundation for the final objective. LeJEPA is simply predictive loss plus SIGReg, and that's it. The prediction loss encourages different views to recover a shared mean representation. The SIGReg loss enforces the optimal isotropic Gaussian structure. A single trade-off parameter, lambda, controls the balance. No heuristics, no teacher-student networks, no stop gradients. The entire core implementation is under 50 lines of code, and yet the design is grounded in rigorous theory. One of the most powerful consequences is that LeJEPA's training loss becomes a reliable indicator of downstream performance. Self-supervised learning used to be a black box. You needed labeled data just to know if your model was good. Now, the training loss correlates extremely well with actual downstream accuracy. In fact, the correlation reaches more than 94%, and even higher with simple scaling. For the first time, researchers can select models without using labels. LeJEPA is stable and performant across more than 60 architectures, from ResNets to ConvNets to VEETs. Small models consistently achieve strong performance on ImageNet 10. Even a massive 1.8 billion parameter VEET-G trains smoothly with beautifully stable loss curves. Bounded gradients remove the need for hacks like register tokens. This level of robustness means the method can generalize across domains and hardware. This principled design unlocks true in-domain pre-training. Many specialized fields, like medical imaging or astronomy, don't have huge natural image datasets. Because LeJEPA is stable and lightweight, you can pre-train directly on your domain's data. On the Galaxy 10 dataset, LeJEPA models outperform large foundation models like Dino v2 and Dino v3, even in low-shot settings. This challenges the assumption that general-purpose models are always the best starting point. LeJEPA also shines in few-shot transfer learning. It matches or exceeds performance on fine-grained datasets such as Flowers 102 and Food 101, but does so with only 100 training epochs, 3 times fewer than iJEPA. This means far lower compute costs without sacrificing performance. Efficiency and simplicity are the core advantages here. Perhaps the most revealing result is the emergence of semantic structure. By visualizing the final layer representations, we see clear grouping of objects versus backgrounds. Warm colors highlight salient objects, like a dog's face or a parrot's body. Cooler colors capture the surrounding context. This spontaneous separation shows that LeJEPA learns deeply meaningful features without ever seeing labels. These meaningful features extend into video. Simply thresholding the self-attention map of the CLS token yields accurate segmentation masks. The pigeon mask, shown here, is created with 0 segmentation labels, and across video frames, these masks remain coherent, enabling zero-shot object tracking. All of this emerges naturally from enforcing a stable, optimal feature distribution. So here's the bottom line. The field has leaned on heuristics for too long. The authors provide an axiomatic, mathematically grounded solution. They prove that the isotropic Gaussian is the optimal embedding distribution, introduce SIGReg as a tractable way to enforce it, and combine both into a clean framework with no hacks and no collapse. LeJEPA offers stability, scalability, and simplicity, fewer than 50 lines of core code supported by solid theory. It's time to build the future of self-supervised learning on foundations, not fixes.